I'm often asked, why do we do astronomy? I'm first asked, am I an astrologer? And I have to say that, although I'm Astronomer Royal, I don't do the Queen's horoscopes. But having told people that I'm an astronomer, I would try and list reasons why we do astronomy. And I thought I'd start off by saying what these are. Simply, the first reason is exploration, to find out what's there. And secondly, to try and make sense of it, to interpret it in terms of the physics we know, and perhaps some new physics. And then perhaps we want to perhaps understand cosmic evolution on a grand scale, to understand how, from a simple beginning, our universe evolved into its present complexity of stars, planets, and people. And perhaps, if you want to be more philosophical, can we understand the key properties of our cosmos in any deeper kind of way? So what I'll be doing in this talk is trying to illustrate all four of these motives for doing astronomy and cosmology. But I thought I'd start with a couple of flashbacks. This picture was taken in the early 1930s in Cambridge when Einstein was visiting Eddington. I don't know what they were talking about. They could have been talking about the famous eclipse expedition, which confirmed Einstein's theory, and which was led by Eddington, and the centenary of that is just this month. They could have been talking about that. They could have been talking about cosmology. But cosmology had very little basis then, because they didn't even know at this time, in the early 30s, that the universe was expanding. We learned, thanks to the work of Edwin Hubble, that galaxies, the further away they are, the faster they're moving, illustrated by these longer arrows. They didn't know that. And indeed, although there were some theoretical models for what a universe might be like in the 20s and 30s and 40s, it wasn't really until much later that it became possible to actually discriminate among these theories. And this picture was taken in the mid-50s, and this shows on the left-hand side Fred Hoyle, who didn't believe in a Big Bang at all. He believed in the so-called steady-state theory, where the universe had existed from everlasting to everlasting. And on the right, Lemaitre, who was a Belgian Catholic priest, but the first person who in the 1920s thought seriously about the Big Bang. And I'm sure that's what they're discussing in this picture. Well, it was in the 1960s that astronomy really did become a quantitative subject, able to discuss the entire universe. And what I'll be doing is talking about what's happened since the 1960s. Because astronomy has really been on a roll ever since that time, not just cosmology, but evidence for relativity being important, etc., etc. To the extent that we can now, with confidence, talk about cosmic history, back to a Big Bang, and we can talk with confidence, as I'll explain later, back to within a billionth of a second of the very beginning. And astronomers have pinned down the universe's expansion rate and the mean density of its main constituents to a precision of a few percent. And we're learning how cosmic structure, galaxies and clusters emerge and evolve from amorphous dense beginnings. And I think when the history of science gets written, the amazing progress in cosmology since the 1960s will be acclaimed as one of the greatest triumphs. I would say up there with the standard model of particle physics and the genome. A huge collective achievement over the last 50 years. I want to give a flavor of some of this progress and also touch on some new mysteries that have come into focus. If you could look at our Milky Way galaxy from 3 million light years away, it would look something like this. This, of course, is Andromeda, a disk galaxy viewed obliquely with 100 billion stars orbiting around some central hub. And galaxies, of course, are the basic large-scale constituents of the universe. Here's another one. And we know that galaxies are distributed through space. They're distributed not uniformly, they are clustered together. But how much can we actually understand about galaxies, these great assemblages of stars and gas? Physicists who study particles can probe them, crash them together in a big accelerator. But astronomers can't crash real galaxies together. And another problem is that galaxies change so slowly that in a human lifetime we just have, as it were, a single snapshot of each one. But we can do experiments in a speeded up virtual universe. Computer simulations incorporating gravity and gas dynamics can calculate what would happen if two galaxies crash together. And that's done by many people here, and I'll show a rather primitive simulation here done about 15 years ago. This shows what would happen if two galaxies crash together in a sort of train wreck. And this computes the gravitational effects and the gas dynamics here. And I should warn you that this is going to happen when Andromeda hits our galaxy in about 4 billion years. 4 billion. But if you look into the sky, we see things like this. This is a real pair of galaxies. And having done calculations, like the ones I just showed you, we can infer that these two galaxies have got dangerously close. One is pulling out a tidal plume on the other, and if we came back in 100 million years, we'd probably find that both of these had merged together in a single one. The other thing one can do is one can do these simulations making different assumptions about the mass of stars and gas in them. And the most important thing that comes out of those simulations is the realization that galaxies are made not just of the stars and gas that we see, but there's about 5 times as much material in some mysterious kind of dark matter, a swarm of particles which have no electric charge and don't seem to interact with each other, but they are important gravitationally in binding the galaxy together and determining its evolution. And these are, of course, particles whose nature we'd like to find because we still don't know what they are. We can test our theories of galaxy formation and evolution because when we look back into the past, we see them as they were young. And this picture shows a small patch of sky, a few odd minutes across. It would take 100 patches like this to cover the area of the full moon. And with the Hubble Space Telescope, you see in this patch of sky hundreds of smudges. Each of those is a galaxy, many fully the equal of Andromeda or our galaxy, but looking so small and faint because they are very far away. And these galaxies are being seen when they were young. And going back to the Hubble law, they have a high redshift, they have a high recession velocity. Now, when people are told about the Hubble law, they somehow think everything is fleeing away from us. But of course, it need not be. And I think a better model is to think of this lattice. This is an Escher picture. And if you imagine you sat on one of these vertices, you would see the other vertices moving away at a speed proportional to the number of individual links. So if you think of the galaxies being linked together by rods, and the rods all lengthen, that's a good model for the expanding universe, although, as you saw already, the galaxies aren't in a regular lattice, they're clustered together. But you can think of the expanding universe as being the lengthening of the rods, which in imagination you could think of as joining the galaxies. And there's no special center. Wherever you're sitting in this lattice, which could be infinite, you would see the same expansion around you. But what you actually see when you look through your telescope is not a lattice like that, but something which is better exemplified by this other Escher picture of angels and devils, because as you look further out into space, you're looking further back into time when the rods were shorter and everything is more compressed. So this is a better picture of what you actually see. And we can now look very far back. Between the bars there is one of the most distant objects we know about in the universe, and this is its spectrum. This is a tracing of the optical light, and the point I want to make is that the strongest line in the spectrum is the Lyman alpha line of hydrogen, and that's normally in the far ultraviolet, 1216 angstroms, and in this object, it's observed in the infrared. The wavelength is stretched by a factor of 8.1, and that's equivalent to the expansion factor between the size of the universe, the length of those rods when the light was emitted, and now. This object is not a typical galaxy. It's especially bright because it's what's called a quasar. It's got in its center a massive black hole, and the radiation emitted by gas swirling into the black hole outshines all the 100 billion stars in the galaxy. So we have something like this in the center of the galaxy, and we're seeing the radiation from that, and that is lighting up all the gas that gives that strong hydrogen emission. And of course, I must show this. This was emblazoned on the front page of most newspapers a couple of weeks ago. This is a great technical achievement, actually getting a map, as it were, of the region immediately around a black hole in a galaxy which is about 17 million parsecs away. This is a false color. They actually observed the radio emission, a millimeter wavelength, and they presented it this way, but this indicates that there really are black holes in the centers of galaxies. And our own galaxy, incidentally, harbors in its center a black hole of around 4 million solar masses. This is one of the biggest. This is 6 billion solar masses. As I said, the light from the quasar, which I showed you, that gave you this redshifted spectrum, set out when the universe was less than a tenth of its present age. But you might then ask, what happened still further back, before there were any galaxies? And the key evidence here dates back to Penzias and Wilson at the Bell Telephone Labs, who famously, in 1965, discovered that intergalactic space wasn't completely cold. It was warmed to about 3 degrees above absolute zero by weak microwaves. And those were subsequently found to have an almost exact black body spectrum, shown here. This is the famous afterglow of creation, the adiabatically cooled and diluted relic of an era when everything was squeezed hot and dense. And it's one of several lines of evidence that have allowed us to firm up the so-called hot Big Bang theory of the universe. And this is a familiar time chart showing the various eras. One important thing is that the microwave background photons have been propagating freely since the temperature was 3,000 degrees and the universe was 1,000 times more compressed. Before that time, the gas was ionized and it was scattered frequently. So when we look at the microwave background, we actually see back to a sort of surface with a redshift of 1,000. More about this later. But first, let's address an issue that might seem puzzling. Our present complex cosmos manifests a huge range of temperatures and densities, from blazingly hot stars to the dark night sky. And people sometimes wonder about how this intricate complexity can emerge from an amorphous fireball. It might seem to violate the famous second law of thermodynamics, which describes an inexorable tendency for patterns and structures to decay or disperse. The answer to this apparent paradox lies in the force of gravity, because gravity enhances density contrasts and doesn't wipe them out. If you have a patch in the expanding universe which is slightly denser than average, it'll lag behind more and more and eventually condense out. Many simulations have been made about parts of a virtual universe, and this shows an example where the expanding universe is scaled out, and you see the density contrast growing. And in this particular simulation, the blue is the dark matter, and the red is the galaxies, made of ordinary atoms, of course. And there's one very important point. The simulations which are fed into So the initial conditions which are fed into the simulations which give rise to galaxies like those we see are not made up arbitrarily. They're derived from observations. Because what we now know from these wonderful observations is that if you look at the microwave background across the sky, it's on average about 2.7 degrees, but it varies in temperature by 1 part in 100,000. And if you do a contour map, you get something like this. And this is a map of the whole sky made by the European Planck spacecraft, and the contours show the hot and cold regions, but the range is only about 10 to the minus 5 of the temperature. But the important point is that if you feed into your computer fluctuations when the universe was about 300,000 years old, which have these properties, and then run the computer forward, you end up with galaxies being structured like we observe. And this is just a picture that shows that. The solid curve shows the predicted RMS density fluctuations as a function of scale. And there's a whole set of types of data which give you the data points, and they essentially fit with this model. But there's one point which complicates things a bit, that the fluctuations which are shown by Planck, if you analyze them carefully and look at their spectrum on different angles, you find that they are not just white noise, they have certain peaks, there are certain angular scales where the amplitude is largest. And this is a picture which shows the latest data as a function of the multiple moment, which is the angular scale. So small angles on the right and large angles on the left. And what's rather wonderful is that this general shape can be calculated. It's caused by the oscillations, sound waves in the universe at an early time when the matter and radiation are coupled and they oscillate like a gas. And the biggest peak there corresponds to a sound wave which has just been able to make a quarter of an oscillation before the recombination. And I'll come back in a bit later to explain why that's a very important observation.
What is this a graph of?
Sorry, it's a graph of the amplitude as a function of angular scale.
With the amplitude of what?
So the delta T over T. The temperature fluctuation. Yes, so it's analysis of the.
Okay, this is all about the CMB.
Yeah, sorry, yes, I should have said it. Yes, so it's really analyzing this data and looking at the amplitude on different wavelengths. Yeah. Sorry? Yeah. Okay. So let me go back to the time chart. We can trace back to the time when this radiation was last scattered, that's 300,000 years. We can also, incidentally, trace back to a few seconds, and that's when the processes happened that made the elements hydrogen, helium, and deuterium. So you've got confidence going back there. And we can probably confidently trace back to about a trillionth of a second. That's a time when every particle in the universe had the kind of energy that can be produced in the Large Hadron Collider, the biggest accelerator in Geneva. But questions which are fundamental like this: what caused the fluctuations? Why does the universe expand the way it does? Why does it contain the observed mix of atoms, radiation, and dark matter? These can't be understood unless we extrapolate back to still earlier times, briefer instants, when the universe was hugely more compressed still. And at this stage, I should put in a warning sign, because when we go back to within the first nanosecond, we are considering conditions which are beyond any direct experiments. All the particles are more energetic than those we can produce in an accelerator. So everything is now rather more speculative. And indeed, according to a popular theory, to explain why the universe is expanding the way it is and where the fluctuations come from, we have to extrapolate back from the time when the universe was a nanosecond old, and that's when the entire observable universe will be squeezed down to the size of our solar system, right back to a much, much earlier stage when our entire observable universe will be squeezed down to literally that size. And a theory called inflation suggests that the expansion of the universe and the structure of the universe was determined by something which started off of microscopic size and expanded to about the size, that sort of size, and then went on from there. And amazingly, if this theory were correct, then the fluctuations spread across the sky and observed by the microwave background, which are the seeds for galaxies and clusters, those fluctuations would have been quantum effects produced when the entire universe was of microscopic size. This is the theory called inflation, and I should say that it's a theory which has some corroborative evidence, but obviously it's not battle-tested because the physics back at the relevant time is far beyond what we can directly test. Now, let me turn to the future of the universe. About 20 years ago, cosmologists had a big surprise. It doesn't change anything I've said about the early universe, but it does alter our perspective on the far future. At that time, it was quite well established that there were three scenarios for the expanding universe, and they're shown here where time's plotted upwards. The universe could expand, and gravity could slow it down to a halt, and it would collapse back to a big crunch. Or it could decelerate, but the mean density might not be enough to bring the expansion to a halt. Or the third possibility is that there might be some extra force, a force which Einstein postulated. He called it the lambda, the cosmological constant, which actually counteracts gravity and causes the expansion to eventually accelerate. And what happened about 20 years ago was that people had to change their view, because most people thought that we were going to have that middle scenario, because we knew enough about the average density of the universe in ordinary atoms and in dark matter to know that it was only about 30% of what would be needed in order to bring the expansion to a halt. So we were in the middle one, not the left one. But the big surprise was when astronomers found that the universe was actually expanding slower when it was half its present age than now. It was actually accelerating. And they did this by looking at a so-called standard candle, at a particular type of supernova, at particular distances, and how bright it appeared. And this was evidence that the universe was on that third type of trajectory, where it was now in a state where this cosmic repulsion, a mysterious force in empty space, was overwhelming the gravitational pull of every galaxy on every other. And if I can just make a slightly more technical point, going back to this, there is another line of evidence which corroborates this. I mentioned that the high peak here, which is on an angular scale of 1 degree, is due to a sound wave, which has the maximum amplitude when the recombination occurs. And this is a sort of rigid rod in the universe. And if the universe had hyperbolic geometry, as it would have if the mean density was below the critical density, the angle on which this peak would appear would be less. And the fact that it appears there indicates that the universe is flat in the sense that the angles of the triangle are up to 180 degrees. And this, by itself, tells us that there must be something in the universe which makes up the other 70% to make the universe flat. Moreover, that something else has to have negative pressure, because it dominates the universe now, but it can't dominate in the past, otherwise galaxies wouldn't have formed. So it has negative pressure. And this means that we would have had to get the acceleration as a conclusion. We have the Hubble diagram, but also, even if we didn't have the Hubble diagram, we could have reasoned that the dark matter was only 0.3 of the critical density, and something else was happening, and that something else had negative pressure. And in Einstein's equations, negative pressure implies acceleration. So in fact, the people who observed the microwave background could have predicted that the universe was accelerating. And I want to show here the data that they already had in the late 1990s when the when the supernovae were studied, and the data wasn't very good, but we now have that as a corroboration, because the fact that that peak is on a scale of 1 degree, an angle indicates a flat universe, and that in itself would have given good reason for believing that we have an accelerating universe. And perhaps let me just have a sort of curmudgeonly remark here. And the curmudgeonly remark is really that you've all seen probably this pie diagram. Sorry. Which illustrates the proportion of the density in different forms. Dark energy 70%, dark matter about 25%, and everything else 5%. And this has been used to say the most important problem is to understand the dark energy. And of course, it is true that the dark energy is a really, really fundamental problem. It's telling us something about the nature of empty space. I don't think we'll understand it until we have some sort of quantum theory of gravity to understand how space itself may be grainy on some microscopic scale, symbolized here. But in fact, the dark energy, although it's important for driving the universe, it's not very important anywhere else in astrophysics, because it's not important in the early universe. It doesn't affect the way galaxies form, and it's not important inside galaxies or inside clusters. So I think it's slightly misleading to think of the dark energy as being more important in astrophysics than the dark matter. The dark matter is very important. We can't understand galaxies or how they form without it, whereas the dark energy has no particular effect. And I should have said, what about the future of the universe in this scenario where it's driven by dark matter? Long-range forecasts are seldom reliable, but the best and most conservative bet is that we have almost an eternity ahead, an ever colder and ever emptier universe where distant galaxies will not only get further away, but they'll accelerate away, and they'll disappear over a sort of horizon, a sort of inside-out version of what happens when things fall into a black hole. And all that will be left in the very far future will be the remnants of our galaxy and Andromeda, which will emerge together, and their smaller neighbors. And protons may decay, dark matter particles annihilate, occasional flashes when black holes evaporate, and then silence. That's a long-range future, according to the most likely forecast. So, let me now ask another fundamental question. How extensive is physical reality? How big is the universe? Well, I've shown you how far we can see, but the point is that there is a sort of horizon around us which is set by how far light's been able to go in the 13.6 billion years since the Big Bang. But that horizon has no more physical reality than the horizon around you if you're on a boat in the middle of the ocean. There's no particular reason why there shouldn't be lots more galaxies beyond that horizon. And indeed, there are strong reasons for suspecting that there are, because if we look as far as we can in that direction and that direction, then the difference is less than 1 part in 100,000. So that suggests if the universe is finite, then since the gradient is so gentle, it probably goes on much, much, much further. And so I think most astronomers would suspect that the universe goes on several hundred times further than the distance we can actually observe. But of course it could go on much, much further still. Could go on so far that every combinatorial option is fulfilled and that we have somewhere else an avatar of ourselves, maybe taking a different decision than we took. But that could be possible if it goes on that far. But that would be far, far beyond our horizon. But be it as it may, even conservative astronomers are confident that the volume of space-time within range of our telescopes, what astronomers call the observable universe, is only a tiny fraction of the aftermath of our Big Bang. And then there's something else. Some models, like inflation, predict that our Big Bang could be just one island in a vast archipelago, one Big Bang among many. And that's indicated, this is just a cartoon, but it shows here our universe, our horizon and galaxies beyond that horizon, but this is just one domain of space-time among many others. And lots of variants, in particular, the Stanford cosmologist Andre Linde has had an idea called eternal inflation, which is a specific model where you have an expanding substratum and big bangs, as it were, condense out. So you have a sort of eternal process which produces big bangs. And this is at least a tenable view, and there are other models of that kind. And so what this means is that we really have this decision tree, which is a challenge for 21st century science. How many big bangs? Is it just one, or are there many? And then a second question, if there are many, we'd like to know, are they all governed by the same physical laws? Or do they display variety? So that what we call the universal laws of physics, which apply in the most distant galaxy we can see, would, in this grander perspective, be just local bylaws governing our cosmic patch. This is an idea which is being discussed by a number of people, because if there are many big bangs, many string theorists think that there are many possible vacuum states, so different big bangs could cool down with different vacua, and therefore different physics. And so this is a possibility, and I think these are entirely open options at the moment. So if that's the case, it means to know what range of laws and constants allow interesting complexity. We know in a universe it's allowed us to exist and allowed a huge complexity, but we'd like to know what range of values for the fundamental constants does allow this sort of complexity. Are we in a very special universe, or could there be other, even more interesting universes? And this is what's called anthropic reasoning. And some physicists foam at the mouth about this. They think that it's really absurd to talk about these other universes. And I'll try and explain later why I think it's not absurd. But for those who are allergic to the idea of other universes, I would just say that it may be of interest to explore what it would be like if the laws were different, in the same spirit as some historians explore counterfactual history. They might ask, for instance, what would have happened if the Brits had fought rather better in 1776? Or biologists may ask what would have happened if the dinosaurs hadn't been wiped out. So I think even those who don't like the idea of a multiverse with many big bangs, they might find it interesting and develop their intuition by thinking about the possibility of slightly different universes from ours and what they might be like. So I'm going to say a little bit about those. And I'm going to put up two successive versions of my hazard sign, just to illustrate this is doubly speculative, of course. But I want to talk a bit about universes that are slower, smoother, more chaotic, and darker and less polluted than ours. Well, the first thing to ask is, what would happen if the gravitational constant were different? We know that gravity is a very weak force. If you take two protons, the electric force between them is larger than the gravitational force by about 36 powers of 10. And that's why, of course, if you're a chemist, you don't have to worry about the gravitational effect between the atoms in a molecule. And I'd like to show this picture. This is a standard pedagogical picture, which I drew in a paper 40 years ago, which shows on a log plot upwards masses and along horizontally the radius. And it's a very extended scale, as you will see. There's is there a pointer here? Yes. Oh, yes, right, yes, right. Yes, so you see here's a proton and hydrogen atom there, and solid objects of ordinary densities, they're on a line of slope 3 in this log-log plot. This is the quantum uncertainty, Compton wavelength. This is a black hole line, slope 1 on the log-log diagram. And because gravity is so weak, a black hole, the radius of a proton, has a mass of about 10 to the 38 protons. And if we go up here, then we have solids, but when they get sufficiently big, gravity makes them round, and then when they get up to the scale of Jupiter, they start getting crushed, and we get into the domain of the stars. So, and I should say also that another important scale, which is important for quantum gravity, and maybe this is important for understanding of dark energy. This is the mass whose Schwarzschild radius is the same as Compton wavelength, the Planck scale here. 10 to the minus 5 grams, 10 to the 19 proton masses, and 10 to the minus 19 proton radii. So this encapsulates a lot of physics, and it's a nice pedagogical diagram. But I want to make 2 points. The first is that the fact that there's such a big scale between the microworld and objects where gravity is important, stars and planets, is because gravity is so weak. And indeed, if you were a theorist who'd never seen a star, then the definition you might give of a star is the assemblage of that number, the gravitational fine structure constant to the minus 3/2 of baryons there. About 10 to the 57 baryons make up a star. Now, this is a slightly expanded picture, which anyone who's taught courses on stellar structure will know. It's just an expanded version of the top part of that picture, which is this is planets, Jupiter, neutron stars, radiation pressure dominating, etc., H burning. But the point I want to make is that if you made G weaker, then you'd still get this pattern, but it would be on a much bigger mass scale. The number of baryons in a star would go as G to the minus 3/2. And otherwise, things would be fairly similar. So the main difference is that the stars would be bigger, heavier, but you'd still have gravitationally bound fusion reactors, and they would live for much longer and last longer. And indeed, although it's not so obvious, if you had this universe where gravity was weaker, it would expand more slowly. One thing it would change is helium abundance, but galaxies would stay, they'd scale the same way. So the number of stars in a galaxy would be the same. So you could imagine a universe where gravity was, say, 10 times weaker, stars would be about 30 times heavier, galaxies 30 times heavier, and they'd live for longer. And this would be a perfectly good universe. So there's no particular fine-tuning in the gravitational constant. All we can say is that gravity must be very weak in order to have many powers of 10 between the scales of the microworld and the scales where gravity is important. But the universe might be even more interesting if it was still weaker, because then you could have more time and more space. So let me think about a second number, which is slightly more interesting. I mentioned that the fluctuations in the microwave background were about 10 to the minus 5. They're not simple. I showed that they differ on different scales, but there's this measure of the roughness of the universe, which is 10 to the minus 5, and this is normally a number called Q, which measures the smoothness. And this has a lot of effects. The gravitational binding energy of clusters of galaxies which eventually form is Q times their rest mass. So in our actual universe, where Q is 10 to the minus 5, a cluster of galaxies has a gravitational binding energy of 10 to the minus 5, so its velocity, dispersion, is the square root of that, which is about 1,000 kilometers per second, 1/300th of the speed of light. And the maximum scale of the structures which are nonlinear in our universe now is again the square root of Q. So we can ask what would have happened if we had a universe where it was either smoother or rougher than our actual universe. Well, if it was completely smooth, of course, we'd now just have cold hydrogen, no stars, no galaxies, and no people. But if it was, say, 10 to the minus 6, not 10 to the minus 5, then galaxies would form later, they'd be less tightly bound, and probably they wouldn't form stars so efficiently. And below 10 to the minus 6, then you wouldn't really have any chance of having stars. So if we want to have a universe where stars and planets can form, then it can't be too smooth. Q must be at least 10 to the minus 6. But what about a universe where it's rougher than our present universe? Say 10 to the minus 4 rather than 10 to the minus 5. This would actually be a rather more interesting universe than ours, because you then have structures forming earlier. And for instance, structures as big as a cluster of galaxies would condense out at a redshift of 10, and their gas would cool down because of constant cooling on the microwave background, and so you would have huge disk galaxies with a mass as big as the present cluster, and clusters would be still bigger. So this might be certainly a more interesting universe with a bigger range of structure. But if you go still further and have Q of 10 to the minus 3, then what would happen is that huge structures would condense out early on, and they collapse to be huge black holes. So you probably wouldn't have any galaxies. So what this means is that the range of Q, which allows a universe where stars and galaxies can exist, is not too narrow. Again, there's no fine tuning, but it's between 10 to the minus 6 and about 10 to the minus 3. Suppose you had something even more than 10 to the minus 3. Then, of course, you'd have to rethink the idea of cosmology, because the idea of cosmology is based on assuming that we can treat the universe, the part we see, as something which is smooth. So the structures are small compared to the overall scale. It's like an ocean where even the biggest waves are small compared to the distance of the horizon. That's true of our universe now. But if Q was, say, 10 to the minus 2 or 10 to the minus 1, that wouldn't be true. It would be less like ocean waves than like a mountain landscape, where one big mountain could dominate the view. And so then we wouldn't really have cosmology, because cosmology is really distinct from astronomy, because we have a range of structures where we can talk about the average properties of the universe. But the point I want to make is that we have a range of Q. It's again not tuned. Now, what about the constraints on lambda, the cosmological constant? Then we know that it mustn't start to accelerate the universe too early before galaxies can form. And it can't be too negative, otherwise the universe will collapse too soon. So there's some tuning there. But if we imagine 2 or more parameters varying, then we realize that there is quite a big variety that's possible. And let me just take this case here, from where we have plotted along here the fluctuation amplitude, and up here the cosmological constant. Here, this is our universe, and as Steven Weinberg was the first to point out, the actual value of the cosmological constant is about 1/10 of the maximum would be allowed before galaxy formation was suppressed. But if Q is 10 to the minus 4, then you will be allowed to have a lambda 1,000 times higher. because things will condense out 10 times sooner. And so if you consider two parameters varying, then the entropically allowed space is very large. And you might ask, why are we here rather than there? We don't know. So I want to argue that there isn't really very much fine-tuning, especially if you allow different parameters to vary and not just one. And let me now mention just a third counterfactual universe. Of course, we depend on complex chemistry, which means we need to have this binding energy diagram for the periodic table. And let's ask what would happen if we didn't have that. Of course, the periodic table and nuclear fusion is crucial for stars, and that's why we have the whole idea of stellar evolution, where we can calculate, we've known for many years, how stars evolve depending on their masses and leave different remnants. And we know that the process of stellar evolution leads to the formation of the atoms of the periodic table, because a massive star, before it dies, has this sort of onion skin structure, and when it explodes as a supernova, this goes out into space and mixes with interstellar gas, and new stars form in this way. And it was, in fact, in the late 50s that these four people, Geoffrey and Margaret Burbidge, Willie Fowler and Fred Hoyle, really codified this idea, or the essence of it. And this showed how you could understand the production of the elements and, roughly speaking, the proportion of them, the abundance, as a function of atomic number. This was fine up to iron. The high numbers, much heavier elements, they are more difficult to explain, and of course there's been some recent excitement that binary neutron stars, only just discovered to be coalescing, these can be perhaps the origin for elements like gold, which couldn't be explained very well by these four people. But a number of authors recently, in particular Fred Adams at Michigan, they've tried to see how sensitive the production of elements is to particular nuclear constants. If you vary the mass of the electron or the strong interaction, cross strength, etc., what changes? I won't go into that, but I thought I would mention something about a very extreme case, what I call the nuclear-free universe. This is a universe where you assume there's no strong interaction, or at least no sufficiently strong one to allow anything other than protons to exist. There you just have hydrogen, but nothing else. And it's interesting that this would give you a universe that, in outward appearance, would not differ very much from our universe. Because stars would still form, and they would contract, but whereas a normal star contracts until nuclear fusion switches on, these would go on contracting until they became white dwarfs, and then they'd stop. And for a pure hydrogen star, the Chandrasekhar limit is 5.5 solar masses. So all stars less than that, they would go on radiating until they became white dwarfs. More massive stars, they would go on contracting to become black holes. And in fact, this universe might be quite bright because you release a lot of energy going down to white dwarf size, and in making a black hole, you might release even more energy than is released in a normal massive star supernova. So if you looked at this universe, you'd have galaxies, rather like in our present universe, and you'd have stars and Jupiter-like planets, and the universe would not be much fainter than our actual universe. But of course, you'd have no chemistry, no rocky planets, no life. So it would resemble our actual universe only in the sense that a marble statue resembles an actual human being. It would look the same in outward form, but it would have no internal complexity. Maybe one exception will be anyone who's read Fred Hoyle's book, The Black Cloud. You could have that as a complex intelligence in a pure hydrogen universe. But unless you have that, then this would be a sort of sterile universe. So we can imagine a range of universes with different parameters and different combinations. And the main point of what I've said is that obviously some would be sterile or stillborn, but there's quite a wide range of universes which would be very different from ours, but would still in principle allow complexity. And some could be even better, in particular the universe with larger fluctuations or universe with a weaker gravity. But as I said again, for those whose minds are closed to the multiverse concept, this is just an exercise in counterfactual history. And of course, anthropic arguments are irrelevant if the constants are unique. Otherwise, they're the best explanation we'll ever have. And let me illustrate this by another historical throwback back to Kepler. Kepler thought that the orbits of the planets were governed by beautiful mathematics, the nested Platonic solids. We, of course, realize there's nothing fundamental about the orbits of the planets. They're historical accidents, and our planet is just one which is in the anthropic range. It's around a stable star, and it's at the right temperature for water to exist. We don't expect any fundamental formula to determine the orbits of planets. And it could be that if string theories are right and are made different vacua, etc., then we will have to abandon any hope of getting precise exact formulae for the fundamental constants. And some don't like the concept simply because it would render the hope for neat explanations of fundamental physics numbers just as vain as Kepler's numerological quest to understand the solar system. But our preferences are irrelevant to the way physical reality actually is. So we should, in my view, be open-minded about the possibility of a fourth and grandest Copernican revolution. We've had the Copernican revolution itself, then the realization that there were zillions of planetary systems in our galaxy, then there were zillions of galaxies in our observable universe. But we then realize that our observable domain is just a tiny part of some far larger and possibly diverse ensemble. So we would live not in a typical part of the multiverse, but a typical domain in a subset which allows complexity to evolve. And the question is this really a scientific question or not? Some people say, well, we can never observe these other space-times, so it's not part of science. I don't think that's fair, because we can perhaps gain confidence in a theory which predicts them, and then we believe this prediction. Let me give an example. Andre Linde's eternal inflation is well worked out, and it works if the physics of 10 to 16 GeV has particular properties. We don't know if it does have those properties. But we may have a unified theory which does apply to the inflation era, and which is tested by being vindicated in our low-energy world. It might be a theory which is able to tell us why there are three kinds of neutrinos or what the masses are, things of that kind. So if we had a theory which was vindicated and which applied at the inflationary era, then we would take seriously its implications about what happened in inflation. And if it had the properties leading to a multiverse, then we should take that seriously. To give another analogy, we take seriously what Einstein's theory says about the inside of black holes, even though we can't observe them, because we've gained confidence in the theory by being able to observe its validity in many contexts outside. So it's not true you have to be able to test or observe every consequence of a theory. You have to be able to test the theory enough to gain confidence in it, and then you believe it even when you can't test it. And this, I think, is going to be the situation for the multiverse. If we have a theory which we gain confidence in, then we'll be able to ask, what does it imply for the very early universe at these ultra-high energies? And maybe it will apply to a multiverse. And, of course, if we want to ask, are we in a typical universe, then we have to open another can of worms and ask about the measure of probability about different values of the constant. Well, in fact, about 10 years ago, I was on a panel at Stanford where we were asked by the chairman, who is Bob Kirshner, an astronomer, how much we'd bet on the multiverse concept. On the scale, would you bet your goldfish, your dog, or your life? And I said I was almost at the dog level. Andre Linde, who had spent 25 years working on the inflationary model, he said he'd almost bet his life. And later on, being told this, the great theorist Steven Weinberg, he said he'd happily bet Martin Rees's dog and Andre Linde's life. Yeah. Well, Andre Linde, my dog, and I will all be dead long before this is settled, but I would make the point it's not necessarily metaphysics. It's highly speculative, but it's exciting science, and it may be true. And we would be able to test whether it's true if we had a theory which applied at these very, very high energies. Well, just to finish with, and returning closer to less speculative matters, I realize that I'm speaking in the World Center for Computational Astrophysics. So I thought I would make the point that up till now, progress in cosmology and high-energy astrophysics has been owed 95% to advancing instruments and technology, less than 5% to armchair theory. And the one thing that's changing that balance is computer simulations, which have hugely advanced in power and expanded in scope. That's certainly true in studying the expanding universe. It's also been true, as we know, for strong field general relativity. We are able to calculate the gravitational waves from merging black holes, and this calculation was fortunately done before the data came in. We can have relativistic MHD calculations to study the flow around black holes, and we can study supernova explosions without special symmetry, and we can study plasma microphysics to understand shocks and acceleration, etc. And this, I think, is very exciting, and the computational work is certainly taking over, especially in a subject where we can't directly do experiments. And I think this is what we can look forward to in the future. And just finally, the 1960s, when the subject opened up, they were exhilarating for young astrophysicists at that time, because there was so much new that the old guys didn't have a big head start. But I'm not here to be nostalgic, and indeed there are some students and postdocs here, and I want to emphasize that today is an even better time for young researchers. The pace of advance has crescendoed and not slackened. Instrumentation and computer power have improved hugely. And on that encouraging note, I would conclude with a quote from Edwin Hubble. Here he is, heavy smoker, as you can see. And he said in his book, Realm of the Nebulae, only when empirical resources are exhausted should we enter the dreamy realm of speculation. So let me end with that thought and with a nice computer simulation of the present structure of our universe. Thank you very much for listening.